All right, let's start lecture 25. In this lecture, we're going to do 23.4, talk about the reactivity rates of different substituted benzene rings. So we mentioned this in the previous lecture. We're going to talk about it a little bit more today. So we take benzene itself. We know if we add an electron donating group or something that has a partially negative charge or a fully negative charge on it, then we increase the rate of reactivity. So we have a simple methyl group on here. We call this toluene, and we know that this methyl group is donating, and so it puts extra electron density into our benzene ring, and that results in this reacting faster than that. And if we put some type of electron withdrawing group, or that atom that's attached directly to the ring has a partial or full positive charge, we know that the reaction is slower than benzene itself. So for example, I put this ketone on here. This is electron withdrawing. This carbon is partially positive. So we suck electrons out of the ring, making it more positively charged and therefore not as nucleophilic. So these type of things are slower than benzene, and things that are donating put partial negative charges into the ring and are faster. So let's talk about this in terms of the Friedel-Crafts alkylation and acylation. All right, so let's first look at the Friedel-Crafts alkylation reaction. So as I mentioned previously, there are a lot of downfalls to this reaction, and we'll see a couple more of those here. So if we take methyl chloride, aluminum trichloride, which acts as our Lewis acid, we put a methyl group onto our benzene ring. So we get something that looks like this. Based on the discussion we just had, we know that this reacts faster than this. So as soon as this is formed, this is more likely to react with another methyl chloride than the benzene ring itself. So usually Friedel-Crafts alkylations end up in polyalkylated products. We know that once this group gets on here, it's an ortho parodirector. So our two products that we would get would be this dimethylated product where it has an ortho relationship. And then we would get the other product where it directs it to the other side here, and we call this relationship para. So what about if we only want a single alkylation on our benzene ring? Friedel-Crafts alkylation is not the way to go. Again, Friedel-Crafts acylation is your best bet, followed by Wolff-Kishner reduction. So we take a look at the Friedel-Crafts acylation. Alright, so we know in the Friedel-Crafts acylation we take some type of acid chloride, the same Lewis acid that we used in the alkylation, and we get this carbonyl group on there. And so we get a product that looks like this. Based on the discussion we had earlier, we know that this is less reactive than benzene, and so once this forms, this is not going to react faster than this. And so we only get one addition of our carbonyl on there. And so again, this overcomes the limitations of the Friedel-Crafts alkylation. And so if you want to do a single alkylation on a benzene ring, the best way to do it is a Friedel-Crafts acylation, followed by something like a Wolff-Kishner reduction, or a Raney-Nickel reduction, or a Clemenza reduction, depending on if you have other things in your molecule or not. And this would get you to the monoalkylated product. All right, one more thing to say about the Friedel-Crafts reactions. Both the alkylation and the acylation cannot be done on deactivated rings. And so if we have something like this ketone here, and we try and do a Friedel-Crafts alkylation, we're going to get no reaction. And that's because when we deactivate the ring, it's not as good of a nucleophile. And the Friedel-Crafts reactions, this isn't an extremely reactive electrophile, and so therefore we get no reaction. Alright, so we're going to move on to 23.5 and talk about how reaction conditions can impact the outcome of the reaction. So this is only important for benzene rings that have basic or acidic functional groups on it. And so basically that's only going to involve phenol. We know these are weakly acidic. The pKa of this proton is about 10. And so this compound is weakly acidic. And the other compound we'll talk about is aniline, where we have a nitrogen on the ring, and we know these are weakly basic. So I'll talk about that in a second. So when phenol is in water, it has a very small amount of it in the ionized form. And so this is an extremely good activator. And so even if we have a little bit of this floating around, we're going to get poly addition of our electrophile to the ring. So if we add a little acid, like acetic acid, to the reaction, that's going to keep this protonated in this kind of form. And then that's going to not be as good of an activator as this is. And so we're only going to get a mono addition of our electrophile. So this is acetic acid here, so we use that in our reaction. It's going to keep our phenol in the protonated state. So let's take a look at the two different reaction conditions. So we take Br2 and H2O. So there is no acid in this example. This is a really activated ring, so we don't necessarily need a Lewis acid in this case. And we're going to get polybromination at every spot possible. We know that this is an ortho para director, so we're going to get addition at both orthocarbons as well as the para carbon, because in water by itself we have some of this excellent activating anion floating around. And so if we don't use acid, we get polybromination at both the ortho positions and the para. If we do the same reaction, but we throw in some acetic acid, we only get monobromination. Alright, so these are the exact same reaction conditions as before. We have Br2 in water, but now we've added some acetic acid, which will keep our phenol in the protonated state like this, meaning it's not as good of an activator, and so we'll just get a mono addition to either the ortho, a mixture of the addition to the ortho or the para position. And so these would be our two products. And so if we have an ortho para director, we get some addition to the ortho position and some to the para. So now let's talk about aniline, which is slightly basic. Alright, so aniline is slightly basic, so if we have it in strongly acidic conditions like we do for nitration, then we're going to end up with a protonated form that looks like this. And so when it's neutral, it is an activator and ortho para director. So an ortho para director and activator, once it's protonated, we have this positive charge on the atom that's attached directly to the ring. So it becomes a meta deactivator. And so if we do nitration conditions with sulfuric acid, we end up getting nitration at the meta position. So let's take a look at these two different examples here. So we know usually that for nitration we use HNO3 and H2SO4. So we throw in H2SO4. That's an extremely strong acid, and so it's going to protonate this amine, so we have this kind of form. And this is a meta director, so we're going to get addition of our nitro group to the meta position. And so now we would have a product like this. And this would not become unprotonated till we throw in some type of base in a second step. So to get to the neutral product, we would need to throw in like sodium hydroxide. This would deprotonate this to give us the neutral compound. So now we would have this. What about if we wanted the nitro group to go to the ortho and para positions? We want to use a much weaker acid than this. Since this by itself is activating, our electrophile doesn't have to be extremely electrophilic. So if we switch out the acid to acetic acid, alright, so acetic acid is much weaker than sulfuric acid, so we don't get nearly as much of the protonated aniline derivative. And so this ends up going to the ortho or para positions. And so now we have this. So remember that phenols are weakly acidic, and so the reaction conditions can affect the outcome. And anilines are slightly basic, and so again, the reaction conditions can affect the outcome. All right, and one last thing to say about anilines is that we cannot do Friedel-Crafts reactions with aniline. So cannot do Friedel-Crafts reactions. And why is that? We know in the first step of the Friedel-Crafts reaction, we usually take one of the lone pairs on the halide and we attack the Lewis acid. But nitrogen also has a lone pair, and nitrogen is okay with being positively charged, so it would much rather donate its lone pair to the Lewis acid than the halogen would. So whenever you mix these things together, the nitrogen lone pair adds to the Lewis acid rather than the halogen on the alkyl chloride or acid chloride. And so now we get to a species that looks like this, and then this is so deactivated that it's not going to do any further reaction. So we don't get alkylation or acylation like we might expect. Alright, so we'll move on to 23.6. We're going to talk about electrophilic aromatic substitution reactions of di-substituted benzene rings. So previous chapter we talked about benzene where it had no substituents. Earlier in this chapter we talked about where it has one substituent. Now we're going to talk about if it has two substituents and where the electrophile adds. So again, you want to be able to consider the groups on the ring and whether they're ortho, meta, or para-directing, and whether they're activating or deactivating. Alright, so the first thing we'll look at is the regiochemistry, so that's the position of where the electrophile adds, and it's pretty straightforward if the substituents are in agreement. And so what do I mean by that? I mean that if the substituents direct to the same spot, then that's where the electrophile is going to go, and there's no question about it. So for example, we take this di-substituted benzene ring here, and we want to do a nitration. Alright, so now we need to think about where our nitro group is going to go. Is it going to go here, or here, or here, or here? Well, let's think about it. So we know that the methyl group, this carbon has a partial negative charge because it's more electronegative than the hydrogens that it's attached to. It's donating, and so it's ortho-para-directing. And then we know that this down here is an electron withdrawing group. This carbon's partially positive, and so it's a meta-director. If we take a look at this substituent, where's the meta positions? They are here and here. And then if we take a look at this substituent, where are the ortho-para places compared to that? The ortho positions are here, and then the para position is where the ketone's at. So the para position is blocked, we cannot go there. And so these two substituents direct to the same spot. And so we're going to get addition at one of these carbons. To get something like this. So again, if your substituents are in agreement, then that is where the electrophile will go, and there's no question about it. All right, so what if the groups are not in agreement? Then you want to look at the more activating group, because that dictates where the electrophile goes. So we take a look at this ring, we see that this methyl group is activating, and it's an ortho para-director. And we know that this is deactivating, and it's a meta-director. So if we figure out the meta positions for this substituent, the one meta position is already substituted. The other meta position is here. All right, then if we look at this substituent up here, we want to look at the ortho para positions. The ortho positions are here and here, and the para position is here. And so we have things that direct electrophiles all over the ring. But which one of these is the activating group? It's the methyl. And so we don't want to worry about the deactivating group. So we're not going to get any direction of our electrophile to that carbon. Now we want to think about all of these carbons. So this carbon right here is flanked by a group on this side and a group on this side. So it's going to be two sterically hindered. Two sterically hindered to add an electrophile there. So we're going to end up getting a mixture of addition of the electrophile to this carbon and addition to this carbon. So we use this molecule in the nitration reaction. Then we're going to get a mixture of these two products here. So again, when they're not in agreement, identify the more activating substituent, and that's where the electrophile will go. It also will not go in between the two substituents due to steric hindrance. All right, so what about if the two groups are equal? So if we have a methyl substituent and an ethyl substituent, they are both directing, they both have about the same activating ability, and so where does our electrophile go? We're going to get a mixture of this directing the electrophile plus this directing the electrophile. We know these are ortho para directors, and so this group, the ortho positions to that are here and here, and the para position is where the ethyl group is, so it's already blocked. Then for this ethyl group, it's an ortho para director, so the ortho positions are here and here, and then the para position is where the methyl group is, so it's blocked. And so we're going to get a combination of the electrophile adding to here and some of it adding to here. And so we get these two products here. So again, if the groups are the same, then we're going to get a mixture of products where they both direct the electrophile to the appropriate spots. All right, so we talked about two activating groups. What if we have two deactivating groups? So remember when we have one deactivating group, the ring reacts slower. So when we have two deactivating groups, it doesn't really react at all. So we have two deactivating groups in our ring, and we try and do a bromination, we're probably going to get no reaction. And so if we have multiple deactivating groups, our ring is no longer nucleophilic enough to attack the electrophile. All right, last thing I want to mention is the more deactivating groups we have, the less reactive the ring gets. The more activating groups we have, the more reactive the ring becomes. And so if we move across from benzene to this pentamethylbenzene ring over here, the reaction rate increases. So for example, if I had a mixture of all of these in a flask and I tried to do a chlorination reaction, so Cl2 and iron trichloride, this one would react the fastest and this one would react the slowest.